In this video, we are going to talk about analytic functions. This is our overview slide, but since this is a fairly short video, we're going to go straight into our material. First, we have a definition of an analytic function, and a function of f of the complex variable z is said to be analytic at a point z0 if it has a derivative at each point in some neighborhood of z0. So this is a definition we've been using as we talked about the Cauchy-Riemann conditions. So an analytic function is one that has a derivative. An entire function is a function that is analytic at each point in the entire finite plane. So an example, since the derivative of a polynomial exists everywhere, in other words, there's no singularity, it follows that every polynomial is an entire function. If a function f fails to be analytic at a point z0, but is analytic at some point in every neighborhood of z0, then z0 is called a singularity, or singularity of f. And our example is z equals 0 is a singularity if f of z equals 1 over z. As you can see, f of z is analytic everywhere except at the one point z equals 0. So in the neighborhood of z0, it's going to be analytic everywhere in the neighborhood, but not at that one point, z equals 0. Next, we have a theorem, sufficient conditions for differentiability. And I just threw this in because we'll be using this for our example, but this is the theorem that we had seen when we were looking at Cauchy-Riemann. So first, if we have a function f of z equals u of xy plus I v of xy, and this function is defined in some epsilon neighborhood of a point z0, and then suppose, so first, we know that the first order partial derivatives of the function u and v with respect to x and y exist everywhere in the neighborhood, and those partial derivatives are continuous at your point x0, y0. And third, they satisfy the Cauchy-Riemann equations. Partial derivative of u with respect to x is equal to partial derivative of v with respect to y. And the second Cauchy-Riemann equation is partial derivative of u with respect to y is equal to the negative partial derivative of v with respect to x at the point x0, y0. If we know these three things, first, the partial derivatives exist, second, they are continuous, and third, they satisfy the Cauchy-Riemann equations, then the derivative of f exists. In other words, it is analytic. And we have this formula for f prime of z is equal to partial of u with respect to x plus I partial of v with respect to x. And then a few more properties of analytic functions. If two functions are analytic in a domain D, then their sum and their products are also analytic. Second, their quotient is analytic in D provided that the function of the denominator does not vanish at any point in D. In other words, that your denominator doesn't have a 0. And third, a composition of two analytic functions is analytic. And now we're ready to do a couple of examples. Our first example is to consider the function f of z equals z cubed plus 4 divided by z squared minus 3 times z squared plus 1. And we want to determine if this function is analytic and where it is analytic. On our overview slide, when we were talking about entire functions, we used the example that the derivative of a polynomial exists everywhere. So it follows that a polynomial is an entire function. So here we have this top, the numerator, z cubed plus 4, that's a polynomial. And then the denominator, z squared minus 3 times z squared plus 1, is also a polynomial. So we know that these two polynomials are analytic. And we also know from our overview slide, if we have two functions that are analytic in a domain D, then their quotient is analytic in D, provided the function at the denominator does not vanish. So when we look at this quotient of our two polynomials, so two analytic functions, this will be analytic provided the denominator does not vanish. So we have to look and see where the denominator goes to 0. And the points where this denominator goes to 0 is where z is equal to plus or minus square root of 3 and z is equal to plus or minus I, which means the quotient is analytic everywhere at these singular points. And last, I call these 4 points, z equals plus or minus square root of 3, z equals plus or minus I, singular points, because in the neighborhood of these 4 points, the function is analytic. It is simply not analytic at these particular points, at these exact points. So they are called singular points. For our next example, we will look at the function f of z equals cosh x cosine y plus I sinh x sine y, and we'll determine whether or not this function is analytic. The first thing I'm going to do is separate out my u of xy, the real portion of my function, which is the cosh x cosine y, and my imaginary part, my v of xy, which is sinh x sine y. And I have copied our theorem for sufficient conditions of differentiability over here. And remember, differentiability is the same thing as analytic. So if we have the function f of z equals u of xy and v of xy, as we've written here, u and v, and it's defined on some epsilon neighborhood, then if the first order partial derivatives of the function u of xy and v of xy with respect to x and y exist everywhere in the neighborhood, those partial derivatives are, and if they're continuous, and they satisfy the Cauchy-Riemann, then we will know that f prime of z exists. In other words, it is analytic. I have here the partial derivatives now, u with respect to x, u with respect to y, v with respect to y, and v with respect to x. And one thing to note is the cosh x, cosine y, sinh x, and sine y are all analytic. And just if you forget what cosh and sinh look like, I diagram them here. Cosh is this parabola, sinh is this, what is this? It looks like a cubic kind of thing, but it's not, it's sinh. Anyway, and then cosine and sine, of course, you're familiar with. Those are all analytic. And by the property here that we have on our overview slide, if two functions are analytic in a domain, then their sum and their product are also analytic. So in particular, here sinh is analytic and cosine y is analytic, so the product is analytic. So all of these partial derivatives are analytic. So far, we have that the partial derivatives, they exist. Where is this? They are continuous because these functions are, they're all continuous. And last, they satisfy the Cauchy-Riemann conditions. U of x is equal to v of x, and we can see that u of x is equal to v of x over here. Is that right? I want u of x is equal to v of y. I'm sorry. So u of x is equal to v of y. Oh, I wrote them right underneath each other so you could see they're the same. And then u of y, the second condition, u of y is equal to negative v of x. So you can see that is true too. So they're analytic, they satisfy the Cauchy conditions, therefore f of z is analytic everywhere because they're analytic everywhere. In other words, f of z is entire. Next, we will take a look at this theorem here. If f prime of z is equal to 0 everywhere in a domain D, then f of z must be constant throughout D. And this is sort of intuitive from real analysis because the derivative is considered the change. So if there's no change, that must mean f of z is constant. I could have put this on my overview slide, but I was running out of space, so I did not. So you might put it on your overview, but I figured this is something you might remember anyway, and as I said, I was running out of space, so I did not put it on my overview. I'll leave it to you to decide if you would like to. We are going to use this theorem here to do the next example. Suppose f of z is equal to u of xy plus iv of xy, and its complex conjugate is equal to u of xy minus v of xy, and we'll denote that the complex conjugate, f of z, is equal to capital U of xy plus iv of xy. And they're both analytic. Both f of z and its conjugate are analytic in a domain D. We want to show that f of z must be constant throughout D. What we have then is u of xy is equal to capital U of xy. Since it's the complex conjugate, the real parts are equal. And then minus v of xy is equal to capital V of xy over here. Since it's the complex conjugate, the v gets negated. Now, since f of z is analytic, the Cauchy conditions are met. That is, partial derivative of u with respect to x is equal to partial of v with respect to y, and partial of u with respect to y is equal to negative partial of v with respect to x. Similarly, I'm not going to try to say that word. Okay, anyway, since the complex conjugate is analytic, capital U of x is equal to capital V of y, and capital U of y is equal to negative V of x. What we have then is little u of x. Well, since u of xy is equal to capital U of xy, then the partial derivative with respect to x should be equal. So u of x is equal to capital U of x. And then we have that this capital U of x is equal to capital V of y. Now, since V of y is just negative v, lowercase v of xy, that will equal to negative lowercase v of y. So what we have is u of x is equal to negative v of y. Similarly, I don't know why I can't say that today, but partial of u of y is equal to capital partial U of y. And that's because u of xy is equal to capital U of xy. Well, u of y is equal to negative v of x, so that will give us negative v of x is simply equal to v of x. So this gives us u of y is equal to v of x. Finally, if we add this equation, u of x equals negative v of y, to the equation we have from the Cauchy conditions, u of x equals v of y, on this side we get 2 of u of x is equal to 0, which implies u of x is equal to 0. Similarly, I should stop writing this word and then I don't have to say it, but similarly, v of x is equal to 0, which means our derivative then is equal to u of x plus I v of x, which is equal to 0. Since the derivative says there's no change, that means our f of z must be constant. To review what we've covered in this video, we looked at analytic functions. First, we defined what an analytic function is. A function f of a complex variable z is analytic at a point z naught if it has a derivative at each point in some neighborhood of z naught. We said a function is entire if it is analytic at each point in the entire finite plane. And the example was the derivative of a polynomial exists everywhere, and it follows that each polynomial then is an entire function. Next, we said if a function fails to be analytic at a point z naught, but is analytic at some point in every neighborhood of z naught, then z naught is called a singular point or singularity. In other words, in the entire neighborhood, it's analytic just at that one point, that singular point, z naught. And the example is the point z equals 0 as a singularity of f of z equals 1 over z. We reviewed this definition for sufficient conditions of differentiability from our last video. And we said if we have our function f of z, which we could write as u of xy plus I of v of xy, if it's defined in some epsilon neighborhood, and if the first order partial derivatives of the function with respect to x and y exist everywhere in the neighborhood, and those partial derivatives are continuous at x naught, y naught, and those partial derivatives satisfy the Cauchy-Riemann equations, u of x equals v of y, and u of y equals negative v of x, then we conclude that f prime of z naught exists. In other words, the function is analytic at that point, and we have the formula to find the derivative f prime at z naught is equal to u of x plus I v of x. We had a couple of other properties to round things out. It's very similar to the properties we had for real valued functions in first year calculus. So if two functions are analytic in a domain D, then their sum and their product are also analytic. And we had an example of that with the cosh and the sines and the sinh and the cosines. Their quotient is analytic in D, provided that the function at the denominator does not vanish. In other words, we want to prevent a division by 0 at any point in D. And then the composition of two analytic functions is also analytic. So that's it for this video. Thank you for watching.